mean, all of that kind of stuff. It is extremely useful. So you type in RS space, and then you can do different things to find, documentation.
That's pretty handy.
Yeah.
I'll definitely check that out.
Search extension. Like when I was just doing the struct opt thing, right? I type in RS space, and then I just say struct opt, and then it jumps me right to it.
That's pretty handy. Thanks for the tip.
And see, if you even read it, as Plat version 3 is out now, the struct opt features are integrated into it. So that all that stuff is new with Plat version 3.
So to give you an example of like a project that I worked on, I created the formatter for the Sway language, which is really similar to Rust format. It's modeled very similarly. It uses like RAST and just reformats the code. And then I also, that was like my first big project with Sway. And then right now I'm working on the documenter, which is similar to Cargo Doc, and it just creates the documentation from attribute comments.
So you're using the procedural macro system. You take a token stream and you return a token stream?
We don't do it the same exact way. So we're doing a parse program which gives us the abstract syntax tree, and then we take those the information we get from that, take all the context of a program, and then we're either pretty much the same thing with the formatter or the documenter, except with the documenter we're taking all the context of the type and all that stuff. But the formatter just takes the AST and then from whatever got parsed and then spits out a string back into the file that it was originally from.
Very cool. Yeah, that's so there's like, if you want to get into like macros and crazy things like this, there's the Rust macro book. And Rust tends to have little small books for all these different niche topics. Like, let's say you want to do WASM, there's going to be like a Rust WASM book. If you want to do macros, there's a macro book. The biggest other official documentation though is the what they call the Rustonomicon, which is like the advanced Rust language book. It's going to have all of the different descendant sync indices and all of the documentation. Yeah. All right, we're gonna kick it off.
Yeah. Macros are extremely powerful, but they're really hard to read. For your first few times, they're really tough to read. I've only used them for like creating structs and enums that are the same but just have different names, maybe, or like implementing like a trait that I know I'm going to implement on the same exact structure, but with different names, or maybe for like creating a test suite. Because you can then make tests that you can have for multiple different objects, that sort of thing. So.
All right, so another quick shout out here. I don't know much about this, except I read this is I think down here. Brown Education took the Rust book and they made it more interactive.
That's good.
And included visualizations in it. So if you click on this link down here, you'll see a replacement book format with all the same content. I've never used this. You have to agree to allow them to capture data about your quiz questions, because now you have like interactive quizzes. But check it out anyway. Maybe you like it. It is getting a lot of steam right now. It looks the same though. Maybe I should have one button. This chapter is not part of the experiment and has no modifications. This chapter is not part of the experiment and has no modifications. Okay, which one's got modifications? There we go. This one's got modifications, I guess. So we can hit play. Then it says the largest number is 10.
That's also on the last book.
I'm not sure what they're. It's a good question what they're doing different. So they have this one, they only have plain copy on the old one. And on the new one they have whatever that thing is too. Might put into a dead publish. going on here. Thank you. Someone decided to plug the power strip into itself. Not something I considered looking for. There's one of the adapters.
That is ingenious.
I know. Good thing I plugged the computer. Dead. I've been sitting out at Renouche, enjoying the weather before we become scorched earth again. That's better. Oh. So we left off in the last class, we talked about RC. Who wants to sum up what that was? Anyone remember what? Oh, it's been like 3 weeks.
That counts.
It has been a while.
RC counts the amount of owners a particular reference has?
That's right. Yeah, RC is reference counting, right? So essentially we take a data type, right? And we attach to it an internal counter. And then whenever we use that in runtime, we increment the counter. And whenever that counter hits 0, and then drop gets called on it, it looks and it says the counter is 0. Now we have to deallocate, clean up, all of that other kind of stuff. So we covered that in the last class, and then we got, I think, we did ARC as well. We covered that, you know, RC doesn't work in some applications. We have to use ARC. And we're going to pivot today from that into how threading works and why we have to use ARC and how other things work with it. So I think we covered ARC in the last one. It has been a while though. So let's do the fearless concurrency. Let's go ahead and kick it off. Rust has a concept of threading, which is actually really nice. The implementation of threading is really nice in Rust. The threading library in Rust is essentially kernel level threads. So Rust doesn't implement much of an abstraction over threading that you see in other languages. Python, for instance, has a very fat threading model, so does Perl. With Rust, they're actually native threads. So this has both pros and cons to it. One of the pros is you have that kind of control, and you can actually run the same type of memory safety checks that you would run in a single-threaded application. They transparently work in a multi-threaded application. And Rust does this all with different traits. So we're going to go over some of those today too. When you take an application and you want to run it inside of multiple threads, you'll use a couple of Rust primitives to make that happen. And I will say that when you're new to Rust, this is very easy to do and it's very appealing. But as you become better with Rust, you find yourself doing it less and less. And that is because I don't believe advanced Rust users tend to use the native primitives for like threading nearly as much as they use something called Tokyo. So Rust has a higher level threaded abstraction called Tokyo, and the whole Rust ecosystem outside of like, like I would say very low level stuff uses Tokyo. So before we dive into this, I want to cover that because I feel like if I don't cover that, people are going to do a lot of things with threads that they don't have to do. So there's something called Tokyo with Rust, or Tokyo. Hard to pronounce it both ways, but I'm going to keep saying Tokyo. And what this is it's a system with Rust that is built on different primitives, and it takes care of a lot of the dirty work for you. So it gives you a runtime, right? It gives you hyper, which is like an HTTP abstraction layer. And this covers both HTTP 1 and 2, and I think they're working on 3 as well. Tonic, which is something I've never used. This is an RPC thing. Tower is used everywhere. And we'll go over some of these technologies probably later on, but not today. This MIO is like how you do input-output, but in an asynchronous fashion. Tracing, this is really useful for like when you want to do logs, you'll use this. This integrates everywhere. So Rust has one system that handles all asynchronous logging done through Tokyo. So when you use something like, let's say you want to build, for instance, here's a case where I was using this. You want to do something that downloads from a website, right? Or makes a request to a website. And then you want to serve that up modified to your user, right? This is very typical. Your website is going to make an API call to another web service, right? You can use something like request, which is like an HTTP client for us that runs on Tokyo. And you can have a web server using Axum, which also runs on Tokyo. And then you have one method that you can do logging on both of them. And it'll tell you, like, this asynchronous call took this much time. So it gives you a unified logging method that works across the whole stack. This is not something you would get if you were writing all of your code with Rust primitives. You know, if you're using Tokyo, you get it. And then this, I've never used this. It's the core. I guess that's just talking about how the raw stuff works in Tokyo. The primitives in Tokyo work. So now we're gonna take a look at how what Rust provides for this. And again, this is lower level than most Rust programmers write code at, right? Most people just use Tokyo for everything, but Rust has native operating system threads. So we have this concept of how we're gonna structure our app. And there are a few different methods that Rust will cover in this section. One of them is going to be a thing called the mutex. And a mutex is pretty simple. It gives us the ability to lock a block of memory, right? So a mutex is going to say, this block of memory is in use by this thread because I've locked it. And then something else will wait on that lock. And then when the lock becomes available, another thread can actually lock that piece of memory and read it or write it. There's another thing called a read-write lock, which is like a relaxed mutex, and that allows you to have multiple readers from that block of memory at the same time. So it's again trying to say, this is a piece of memory that I want multiple different threads to access, and we're going to get around the complexities of that by locking it whenever we need it. So I lock it when I need it, and I unlock it when I don't need it. So that's one method that you can use to do threading in Rust. Another method you can use to do threading in Rust is message passing. And this comes from other languages like Erlang, but it fits really well with the Rust model. And Rust provides these primitives to where we can essentially pretend like data that we're sending to and from different threads is like a message, right? So we send a message into a thread, and then the message can send something back on a different channel. And these methods of arranging these channels is another method in which you can structure a multi-threaded application. And there are other methods too, but you know, we're not going to hit them all. Generally speaking, when you're structuring an app in Rust, this is overwhelming, right? There's too many design decisions you have to make. So what you'll tend to do is copy and paste an example from whatever thing you want to make. So if you're making like a website in Rust, you're going to go to Axiom, you're going to copy and paste the Axiom example, and however that example is structured, you're likely going to continue that forward. You know, so these types of design paradigms are not things that you really have to be too familiarized with. So there's complexities behind threads, right? Does anyone here not understand what a thread is or what it's doing? I kind of came in hoping that everyone would have some. Does anyone not understand what threads are?
I don't understand what a thread is.
Cool. So the way that Linux works is it takes all of the things that you're running, and it has a unique name for that thing, right? It's called a process internally. And a process internally can have multiple threads, right? So a process is, I would describe that as the smallest component, right, of a task, and of something some work that needs to get done. And a thread is really like an atomic that thing can use to arrange it. And the reason why threading is useful is because sometimes you want to have one thing done, and you want to make use of all of the cores on your machine to do it. So normally, if you have just one thread per task, right, then you can only make use of one core in your machine. So you've got like, it looks like you're running on a MacBook.
Yeah.
So you probably have like, let's say between 4 and 8 cores on there, right? So if you want to make something run on all 8 cores, you want to computationally utilize that Mac to the fullest, you're going to have 8 different threads that the CPU can schedule on each different core, right? That the operating system can schedule on each different core. And that's where this comes in. So if you write a program in something like Ruby, Perl, Python, PHP, any of these languages, right, they will not make that program you write multi-threaded, right? That's not something that they do out of the box. So when you run those programs, they're only ever making use of one core in that machine. You say, okay, well, I bought 8 cores. What does that mean? That means that you bought 8 cores so you can run 8 different things at the same time. But any one thing you run, unless it's written to be multi-threaded, will not make use of those other 8 cores. Those are the other cores that you've got. So this is a method in which you can make one program take all of those 8 cores.
Why would you want to do that though?
Well, that's a great question, and to be honest, most of the time you don't want to do it, and that's why languages that are very popular are so bad at this. Because the use case for wanting to do this is relatively small, but when you need it, it's absolutely massive, right? So most of the work that you do on a computer is bound by something called input-output. That means you're talking to like a web server, you're talking to a database, or you're talking to something like that, and you're waiting on that thing to respond to you. But it's not always the case that you're waiting on something else to respond to you. Very often you're literally bound doing actual thinking work, right? So an example of this would be like if you're doing image processing. If you're doing image processing, you have an image, and you're running an analysis on that image, you may want to use all of those cores of that machine to analyze that image, because you're not waiting for anything else. The faster you can analyze it, the faster you're done. So Rust gives us an ability in which we can make one task multi-threaded and assign those different threads to different cores. That's what the operating system will do. To answer that question in a different way, right? Think about it like this. If you take a program you're making and you're bound by I/O, multi-threading doesn't matter. The majority of programs that you write, as a software developer, can be bound by I/O. If I was to take a guess, 90%. The 10% of the time, when you're not bound by I/O, you will always, by default, it's the only other option. You're bound by computation. And that's where multi-threading comes into play. Thanks. No problem. Did that make sense?
Yeah.
Cool. All right. And another way, too, that you could say it is even when you're not bound by I/O, even though this is more work to write a program like this, and it will likely cause you somewhat more grief, it's not bad to start it. What's up?
I can give a real example of software you improve mine.
Sure.
Well, going back to the stock trading app, there's like 1,500 stocks. It's doing linear regression calculations, all of them, right? If you just run it on a single core, it takes about 5 minutes to calculate all the linear regressions and the errors over like a 10-year history. It's all done in SQLite. But when I added when I split it across 8 threads, it reduced the time by around 5x. When you increase the number of threads, it doesn't linearly increase it. Like I didn't get 8x improvement, I got around 5x. And actually, it turns out the program runs in SQLite, but in SQLite, after you go past 8 threads, it just there's no improvement.
You generally want the most you can parallelize is the amount of cores you've got. So it's going to be separate for each machine. If you had a 32-core machine, likely you could get some kind of improvement by going past 8 threads. But if you only had 8 threads and you put, let's say, 16 threads on it, you say, I want to run this program, it needs 16 threads. My machine only has 8 threads. What your computer then does is it juggles between them. It says, okay, you get some time, you get some time, you get some time, and then this act of juggling ends up taking more work, right, than reducing the thread count, because then you don't have to keep all these balls in the air. But the act of juggling, too, is why you want a multi-threaded machine to begin with, a multi-core machine to begin with. Because when you have a machine that has 8 different cores on it, then your machine, your operating system, doesn't have to juggle that for each different process. You can have 8 different tabs in Chrome all doing something, they're all single-threaded, and your Chrome can say, all of these are going to get different threads to operate on, and your operating system will put each one of those different threads on a different core. Okay, so here's how it looks like in Rust. We talked about this syntax earlier. Does anyone remember what we called this right here?
Okay.
That's right, exactly. So Rust does threading by essentially providing it a closure, right? And that closure has the ability to close over the arguments that it exists in. In this example of a closure, there is nothing that it's closing over. And you know that because in Rust, in order to close over something, well, again, does everyone remember copy and clone? This comes back to that. If you're closing over something that is cloned, you have to move it inside, right? Copying will work transparently. So it's the same type of thing we saw before with other closures. But, so here's the closure, and what we're doing is we're saying, we wanna spawn a different thread, so now that the operating system is gonna say to the kernel, or rather, the instructions that will be compiled will say to the kernel, spawn us a different thread, and inside of that thread, run this code right here. For I in 1 to 10, print this I number from the spawn thread, and then sleep, right? So what they're going to be showing you here is that this truly happens at the same time. And what you're seeing down here is that you see one from the main thread, one from the spawn thread, two from the main thread, two from the spawn thread. And this is all happening, well, down here is where you can actually see it go haywire, right? Because now we're just seeing hello 5 from the spawn thread. So we're getting these out of order, right? This is actually not a very good example. But I'm gonna tell you what they're trying to show. They're trying to show you that these high number 4 from the spawn thread and high number 5 from the spawn thread, these are both coming in out of order, right? You're seeing these things tick off. And the reason for that is when a thread is working, there's nothing that guarantees that one thread won't finish faster than another thread, even if it starts later. Why? Because the operating system may put something on one of those threads, like your music player, and it may get a slice of time. And that will result in another thread running later.
They're also showing the first thread doesn't even finish. It goes to 10. And the process exits before that thread even finishes. Ah,
there we go, yes. So when you spawn these threads, that's also a really good observation. When you spawn these threads, if you don't tell your main thread, the one that spawned them, wait for all these things to finish, then what ends up happening is your main thread can finish first, and it won't even check up on them, right? Processes can also do this, but that's what they're showing you right here. So you have this is your main thread, it's whatever's executing main, and then all of this stuff that happens in it is running in the main thread, including spawning all of these children. And what can happen is the main thread that runs this code can exit before the threads it spawned complete. Right? So this is showing you the complexities of threading. And what we're doing down here is we're solving that with this, handle, join, unwrap. So here we're saying let handle equals thread spawn. We're spawning a thread. This thread is going to do, actually, let's point that out. In both of these, we're only spawning one thread, right? So this is the for loop is inside the thread spawn. So we are spawning one thread here that's going to be printing all of this stuff out. And same thing down here in this example. We're spawning one thread that's going to be printing all of this stuff out. But in the thread we're spawning, in this one, we have this handle, join, unwrap. And what this is going to do is it's going to tell the thing that executes main, do not complete until this handle, right, is complete. So now we're saying, hold up, don't finish until this is done. And that's what we're doing right here. Thread spawn is returning something that we're waiting for. Right? So that's where the blocking happens. And another way to think of that would be when you spawn a thread, there is nothing intrinsic to spawning a thread that says wait for the thread to complete. Right? You may have a thread do work and then you don't care if it completes at all. For instance, if you've got a server and it's listening for some data to come in, it may not be useful to wait if you're killing off the server. Maybe you don't care about having a graceful shutdown. And here's that same code running, and you're going to see here now we have all of the data coming in. So when we wrote for I in 1.10, this is going to print out 1 through 9 because there's no equal sign right here, and that's what we're doing. So now you can see here we're getting all of the spawn threads from 1 through 9. All right, on this one we've modified it slightly, and what we're doing here is after we're waiting, we're printing the rest of this stuff out. So what they're showing you here is that the 1, 2, 3, 4, 5 happens after you've done the waiting, right? That's the big difference here. So if you call handle, join, unwrap, this is where the blocking comes in. Now I'm saying wait for all of my threads to complete. I'm blocking the thing that did the spawning. And then after it's done blocking, we run this code. Now all of these are going to be ordered too. And then that's what they're talking about here. See, so where join is called is going to affect whether or not your threads run at the same time because you're blocking, you're waiting. Using move closures with threads. So this is something that's very nice too about Rust, is that if you ever forget to do this, the Rust compiler will just tell you, you forgot to, this needs to be a move closure. But what they're doing right here is they have a V, which is a vector, and they want to put that vector inside of a thread. And Rust is not going to like that, written like this, because the thread needs to actually own the vector. And the reason for that is, when we talked about how Rust does ownership, what did we say was the main reason ownership exists?
To make sure all the stuff is dropped at the end of the, or it's dropped at the end of its scope or lifetime.
That's exactly right. We have this concept of ownership primarily, right, to determine what can read and write and who cleans up, right? And that's exactly right. So what the problem is with this piece of code, written this way, is that who's going to clean up this vector, right? Who's going to clean that up? Now you have something on the heap. You've got three different integers, right? So you've got three different ends on the heap. And essentially you're saying, I want this thread to have access to it. Now we've already shown in the first example that the main thread can close before the children, right? The main thread can say, I'm done with my work, I'm going to go away, and leave the children, right, alone. The children, normally, you want them to close before the main thread. It's almost always what you want. But in this example, right, the question remains, in the thread that has access to this vector, is it going to clean up this memory, or is the main thread going to clean up this memory? Either one of those two things is possible. The way Rust is written, you move the vector into the thread, and then when the thread is done, the thread cleans up its own memory. So that's what the Rust compiler is complaining about here. It's saying we're running compile time checking on this, so I don't know when that thread will be done. So if you want the thread to do the cleaning up, you have to move it, right? And then these are the errors that you're getting. And just to be clear, like here's the error. It should actually say, to force the closure to take ownership of V or any other reference variable, use the move keyword, and it even shows you what it looks like, right? This is the difference between a move closure and a regular closure. All right, and down here, you can see them actually showing you why this problem would exist, right? So here we have the same vector, we have the same code, and it's still not going to work, and they're trying to show you why that code wouldn't work. And this is actually kind of a good idea, and if I was gonna give the book advice, I would say, that's probably a good idea, a good way to show the whole entire act of borrowing, right? And ownership. If you imagine drop commands in there, you can answer why we have to do a lot of this crazy shit, why Rust is so much more complex. And the answer there is that this drop V, right, if you think about it, the problem is this thread, you don't know whether or not this thread completed to make this happen, right? You may not be able to drop if this lives longer than the thing that spawned it. That make sense? All right. So down here you can see the solution, and this is the same thing that they give us. We just have the move keyword, we're done. And and then here, we're not actually done because they left this code. Oh no, they didn't move this code in here. This one that they're running here didn't work, and it didn't work because they left drop B. So we are dropping them in thread. Oh, but that's just showing what the error is. Anyway, ignore that. Using message passing to transfer data between threads. So this is kind of interesting, and I'm going to show you again with the Rust search extension. std sync is where all of these different channels are. So if I open up a new tab and I go rs space and then I do std : sync, you're going to see the sync modules, and this is where we have all of these different channels defined. So you're going to see down here things that they have for higher level. This is one we're going to be talking about a lot. We'll talk about ARC a lot. But down here you'll see the other modules for multiple sender, single producer. And this is a different method of architecting the program. And this is a very important example to understand if you want to understand channels. So the way a channel kind of works is it gives you an API to communicate with threads. What we've seen thus far is how we get data into a thread. That's only half of the problem, right? There's a lot of work we have to do to make sure we do that safely. But after we get data into a thread, the question still remains, how do you get a result out of a thread, right? So one of the methods to get the result out of the thread is to use channels. And channels give us something we can give to the thread to return us back a result. It's essentially a method in which the thread can call back into you and say, this is my result. So here's how we do it, right? We create this channel here, and it has two different parts, the transmitting part and the receiving part. And then we clone the transmitting part, and we move the cloned transmitting part into the thread. And we can send whatever we want on that wire. And then from the main thread, the thing that is spawning all these, we have this receiving channel, and we just call the receiving channel.receive, and we're going to get the result back. So this example is showing you how you can send and receive one piece of data. Now it gets a lot more complex in actual libraries when you're writing them with Rust, because sometimes you're actually sending channels in with channels. So you start a channel where you can communicate from the thread to the main that's spawning it, and sometimes you want to run communication that way too. So there's all different ways you can do this, but let's go back and this up. So here's what they're showing us here. It's the same thing. MSPC channel, TXRX, and then we have transmit and receive end. And just really quick, what MPSC stands for, this is the one model of thread you'll see everywhere in Rust. It stands for multiple producer, single consumer. So I have multiple things that can talk to one person, right? One different thread, one channel, that's how I'll say it. So this is useful. This is something like when you model different forms of communication, you can have like single producer, single consumer, right? This is me talking to you and you not talking back. In a classroom setting, right? I could have single producer, multiple consumers. The opposite of this. I am talking to many people, right? Well, this is the model that Rust is very familiar with. Multiple producers, single consumer. And the reason why this model is so popular is because you tend to have more threads, right, than main processes by definition. So you're going to give every one of those threads a method to communicate with the main process. To say, I'm done with my work, my job is complete, here's the result. And here's what it looks like. We say thread spawn, and we're moving into it. What are we moving into it? We're moving into it this TX. And then I'm sending with this TX the value, and I'm calling unwrap. And what unwrap is going to do is it's going to say if the parent process exits before me, then this dies. Like, there's nothing I can communicate with. Otherwise, we'll just have a silent value there. But of course, Rust doesn't like that. Okay, so we're here, and now on this example, we create another one of these channels, and we're doing something slightly different here. On this one, we are printing out what we receive. So there's actually a very small difference there. We're saying RX receive unwrap, so now we're getting the received input, and then we're simply printing that out. So this is us doing work in a different thread, which means it can get scheduled on a different port, and then when it's done, it returns the result to us. Now let me say this too. This is stupid, right? This is almost always going to be stupid. Why is it going to be stupid? It's going to be stupid because you have one thread. Right? It really doesn't ever make sense to take a main process, to spin off a thread, to wait for that thread to complete, and then return the result back to the parent. That doesn't make sense because the parent isn't doing any more work, and the child isn't doing any more work, the thing you're threading. So why not just have it all done in the same place, right? So generally speaking, that's like an anti-pattern. If you're going to use threading, you're going to want more than one, or you're going to want the guy that creates the thread to do work. And here's an example of ownership transference. And in this example, what they're showing you is how we're going to move this TX in, right? So this works because we only have, this doesn't work. Yes, okay. Okay, the reason why this isn't working, here, I'll show you what the problem is here. The reason why this example doesn't work is because they are sending this value here, this string, through to the channel. And this channel is running using the same ownership semantics as the rest of the program. So when you send something into the channel, you've changed the ownership of it. And the problem with this is, you can't send this string through the channel, change the ownership of it to the receiver, right? That's who's now gonna own it, and then still have access to it right here. So this does not work for that reason. It's telling you that this value is moved, so you can no longer borrow it. You can't borrow after moving. And in this, am I moving too quick? Is everyone getting this? You picking this up, Josh?
Yeah.
Got any questions on it?
No.
How are you, Max? Good? Okay. We have, in this thread, what we're doing is we're spawning a new thread, and we have this vector with all of these different strings in it. And we say for valid values, so we're iterating over these strings, and we want to say, for each one of these, send them through to the channel, right? Make sure that the channel is alive, and if it's not, panic, and then sleep, right? So we're going to send hi, sleep, send from, sleep, send the, sleep, send thread, sleep. And then as we do that, we're going to iterate over here, right? This is going to be iterable, and we're going to say for received in Rx print, and then we're doing that. So this Rx is up here with the channel. Every time someone sends something through the channel, what you're going to have is this is like an iterable, right? This is something you can iterate over. And in this model, the iterable is returning a message you've received, right? So these are the messages that come in. And what's interesting is, you know, that all of these different threads, this thread you spawn right here rather, is just simply sleeping on you. So when you're waiting for it to complete, you know, that's what's going to happen. The parent is going to wait for all of those to complete. Creating multiple producers by coding the transmitter. Okay, so I just said that it's stupid to have one thread if your parent thread isn't doing anything, because you don't always just put it in a single-threaded application. This is an example of your first multi-threaded application. This is how simple it is. We have a thread at the top that's doing the top work. We have a thread at the middle that's doing, you know, the other work that we have. Now we have two threads, and we have one channel down here that's going to print them out. Both of these threads are going to run concurrently, right? This is concurrent work that's going to happen, and again, it can happen on different cores in your machine. So one core will do the top, one other core will do the bottom, and then one core will wait for them both to complete. And as they complete their work and they send messages, you're going to see those things print out. And because you're sleeping for the same duration of 1 second, right, the differences between when one prints and another one prints is going to be undefined. Because the relationship of work completion with threads is undefined. You never know which one's going to get scheduled last. You don't control that. So we have hi, more from messages for the thread view. And what we would expect is hi, more messages, no, hi, more, yeah, okay, that's really stupid. Yeah, so I just want to see if they're interleaved properly, right? If they're interleaved properly, then this is a really bad example because it doesn't show you the instability of this, right? What I mean is, if you have both of those threads operate, I would not expect the interleaving to be perfect, right? I would expect maybe one of them to be out of order, because that's just how threading works. So if they're perfect, you're going to have this one tick off, and then 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 this one, and the last one, right? If they're not perfect, you may have this one tick off, and then this one, and then this one, and this one, and then this one. You know, you'll see them out of order like that. Of course, when you're using a really big duration, like 1 second, maybe they just don't want to show it. But yeah, so these are actually perfectly done for the thread, yes. See here, you might see the values in another order depending on your system. I think that that's always something important to show, right? It's always important to keep in mind that when you spin off two threads, you are not guaranteed the order in which they're going to finish their work. That's the source of a lot of bugs, that expectation. Shared state concurrency. Okay, so in the last chapter we talked about ref cell and RC, and we said that RC is this method to have like reference counted stuff, and we even talked about how other languages do this for you, and that's why they're all slow and they suck, right? I think it was the conclusion we came to. We showed like Perl uses reference counting, and the downside to this is that everything is slower because now every variable has to know how many things are pointing to it, right? So because you have this overhead, that language is going to be slower than Rust or C, where you don't have reference counting. We also talked about this method of refcell, which is interior mutability. Right? Rust doesn't like you having the ability to mutate data that is shared with other people. Right? So refcell gives us a method to do that in a controlled fashion by making these checks at runtime. And what we said is that the method that we did that only worked for single-threaded applications. Well, to do this with a multi-threaded application, we have to use, rather than RC of refcell, we use this other thing called ARC, right? And an ARC is what they call it atomically reference counted. Does anyone know what an ARC is? Does anyone have experience with an ARC?
I have a lot of experience with ARC.
There you go.
Do you want me to explain like my experience with it, or?
Sure, yeah. Tell me what you know about ARCs.
So I mean, just the way that I used it was when we had some kind of source code where we didn't inherently have like a string that was created already. We're needing to get information about that string. For instance, with the formatter that I created, we used an arc wrapped string of the source code in order to get a reference count of like the length of the source code in order to replace certain things without losing the context of where they were or how they should look. So that's just one example of how I've used it.
Why would you say an ARC is different from a regular reference counted variable?
It's atomically reference counted.
What does that mean?
I don't know.
Okay. Okay. So here's how it kind of works, and we'll keep this, high level. But we can also, I could geek out and show you a lot of this stuff. But so when you work with a computer, the CPU, there are different primitives the CPU has knowledge of. And here's the deal: every different primitive the CPU has a different instruction that you use to operate on it. What do I mean by that? I mean that when you take an integer in Rust, we have what different types? Who knows the integer types in Rust?
I32, I64.
Precisely. Okay. So your CPU has knowledge of all of these different types. That's not something Rust created. Rust is saying most CPUs have these types. We're going to make these types of primitives for Rust, and we're going to give you access to them. In JavaScript, how many different integer types do you have? You also do JavaScript.
You have number.
You have number, right? So in JavaScript, what is a number? Does anyone know?
It's an ambiguous number type, so it could be a float, it could be an integer, it could be whatever.
Right. But the spec says that it has to be able to contain double long. You can make optimizations for it, right? So that's how JavaScript works. JavaScript has one, and Rust has all of these different ones. Well, when you write, for instance, JavaScript number plus one, and you write Rust number plus one, this thing plus, even though it's the same symbol for you, for a computer, it's a different operation entirely. There are different operations to add I32s than there is to add I64s, right? The actual instructions for the computer have to tell you the first thing in this register is 32 bits, the second thing is 32 bits. I want to add all of them, or I only want to add the first 8 bits of them, right? So we have these different types that all these operations are for, the very lowest level of our computer. 8-bit, 16-bit, 32-bit. Okay, well an ARC is none of those, right? An ARC is a whole different another type. It doesn't use anything like that. And what an ARC actually does is an ARC has a method to ensure that when you read it in and you write out the modification, nothing else made a read in between it. That's why it's different. So the act of doing that means that the changing of that type has to happen in one CPU cycle, right? And that component, changing it in one CPU cycle, makes it slower because it's got to lock that register down so nothing else touches it. And the fact that Rust can do that and that it's going to need to do that work makes them slower than other types. So you don't want to use these atomics for everything. But an atomic is a totally different type to your architecture, and your architecture has to support them. Now all of them do. So that's what this is all about. This is all about making sure that the reference counting variable internally uses one of these special atomic types. Otherwise, they're the same. So now you kind of have an idea between the differences here. Now, when we talk about ARC, an ARC is just simply an RC that's atomic. We have another component to that, which is this component of refcell, right? And I said earlier, ref cell gives us the ability to make stuff mutate internally, right? Mutex also does that. The difference between mutex and ref cell is mutex is going to be locking. It's going to have a different API. We're going to have to call unlock on it, right? So we're calling mlock unwrap, and then we're changing the number. And this is actually saying, this piece of memory, do I have access to read it? If I have access to read it, then I can actually write this, or read it and write it. And there are different types of these. There's mutex and another one called read-write lock. They're both very popular. But what they're saying here is, we have this mutex tool, we have this RC tool, this ARC tool, and we're gonna start to use them together to create shared state concurrency. And this objective is, I want to have a block of memory that I share between multiple different threads. And why is this useful? Let's say that you have multiple different threads and they're all participating by generating an image. One of them may want to generate the top quadrant, the other one may want to generate the bottom quadrant. Maybe they all have to know what each one of them is doing at that specific point in time, right? You can use an ARC to do something like that, right? You can have them do work, lock the memory, write their changes, unlock the memory. Then another one can lock the memory, write its changes, unlock the memory, and they can all communicate with this mutex protocol. Interestingly enough, how is the mutex implemented? Does anyone know that one?
No. I've read a lot of code with mutex and with RepCell before, but I didn't write it. I had to read over it for just context.
Sure. So mutex is actually internally, it also uses an atomic reference counted, right? So it's got an atomically reference counted bool, right? And that's called a semaphore. And that semaphore is working and it's saying, is this 1 or 0? If it's 0, I can lock it and set it to 1. If it's 1, I don't touch it. So there's that's how that works. And that's using something called compare and swap, which is super fun. So we're going through this mutex idea. Let's explain this one here. Let's actually go up this one first. We have this where for I in 0 to 10, we are spawning a new thread for each one of these. Now this is the first one where we've actually spawned threads in a loop. Right, so now we're spawning threads in a loop, and what are we moving into the loop? We're moving into the loop a mutex, right? So this is interesting because we can simply move the mutex into the loop. What do? We call dot lock on it. Now dot lock is blockable, right? So while we're spinning up all of these different threads, any thread that can't lock the mutex will block. It'll wait. And then we add 1 to the number internally, and then we push to the handle for it, right? So each one of these different threads is returning something we can wait for. Right? Does it remember why we did this? This is the very first thing we covered. We covered if you want the threads to complete before you exit, you have to take that handle and wait. So what we're doing is we're taking these handles from these different threads and we're pushing them onto the vector handles, and then we're waiting for all of them. And that's what we're doing down here. For handle and handle, join, unwrap. Now we're saying wait for all of them to complete. So we're going to spin up all these different threads. Each one is going to wait for a lock. When it gets the lock that it needs, it's going to add 1 to it, and then it's going to push back the handle that the main thread can wait on. And you're going to see the problem down here with this. So this is the problem. The problem is that the counter, the use occurs due to use enclosure. Okay, so the problem is that this counter here, right? I was wondering why it looks so funky. There you go. This counter here, which is from the mutex, you can't move that one in. What you have to do is say for this in 0 to 10, counter.clone, right? Counter equals counter.clone, and get a different copy of that mutex for each one. And then it'll work. And then that's what they're doing right here. So here, let counter equals rc.clone counter. Now this also won't work, right? This is iterative failure. This is really annoying to teach this way. Why this one won't work though is simply because we've already went through this. This is an RC and it needs an R. So they're just simply iterating and throwing all of these different messages that are failing and what you have to do to fix them. So they're saying right down here, this is the message you'll get if you try to use an RC between multiple threads. It'll very politely tell you, I can't do that. So RC cannot be sent between threads safely. Notice that it doesn't actually advise you to use an ARC here. That's probably not good on Rust, but the reason why they may not choose to do that is because there's other solutions to this problem too. So here's the solution that is very popular, is just using Arc. You can see this is part of the standard library, Arc and Mutex. These are all really very low level primitives. And we're calling it right down here Arc clone counter. So now we have this guy up here, which is an Arc of the Mutex. We're cloning it to get the counter. We're moving this clone in. Then we can lock the clone, add the number, and push the handle, which we're going to wait on. Does anyone have any questions on any of this stuff? I mean, I'm telling you, this is near the end of it, so this is the reason why it's getting hairy. We have this object-oriented programming features of Rust, pattern matching, and then in my opinion, chapter 20 and the rest of these things are probably just totally so far niche, we may not even want to do them, you know? We're getting to the end of it though.
I do remember at one point I was talking to a colleague and they mentioned to me that they had to do some kind of hacky thing to make sure that whenever something was on lock, it wouldn't have like a deadlock, I guess, where something was locked but then it couldn't become unlocked because it depended on something else to be unlocked first.
Sure.
And so you ended up in this cycle, which caused the program to be in an infinite loop, essentially.
So I can go over that really quick. Let's talk about that. All of these mutexes are using this concept of locking, right? So they're saying, I need to get access to a piece of memory. If I can get access to a piece of memory, then do this work. What happens if you can't get access to that piece of memory? What do? They wait, right? Now this creates a real problem, because if two things are waiting for each other to get access to that piece of memory, they will never get access to that piece of memory. And this is called a lock contention. It's a whole series of problems you can have. So you can mitigate this problem in different ways. This is where RW lock comes in. I said mutex isn't the only way to solve it. RW lock only gets a lock when you want to write. Everyone can read, only one person can write. That follows with the ideas of Rust more generally. So you'll generally see mutexes used in educational stuff, and you'll generally see RW locks used more in practice. But lock contentions are a real problem with this design methodology, which may mean you want to rethink your plan. Now, if you're spinning off 40 different threads, and every one of those threads is waiting for a lock, that's a lot of different contention, you know? And another thing that you generally speaking want to do with the mutex is you only want to lock it for the shortest period of time when you're writing, right? So if you have the ability to lock it for the entire thread execution, you have a larger footprint for lock contention. If you lock it only when you're writing, you have a very small footprint for thread contention, for lock contention. That's a totally valid point, and a real pain in the ass when you find it. And when you find that class of error too, deadlocking, Rust provides almost nothing to help you, or rather to see, solve that problem. Okay, that's cool. And the real solution there, by the way, is just simply never use mutex. I mean, I always say, like, if you get to the point where you're using mutex, just say, how can I do this a different way?
I don't think I think I've seen mutex, now that I'm thinking more about it. I think I've only ever seen RW lock, Arc, and RC in actual practice, and then I remember reading about mutex as another possible type of atomic or preference counter.
Sure. And if you really want extra added complexity, there's a mutex in Tokyo, and then there's a mutex in Rust, and they're different. And then there's also one in a high performance library called Parking Lot. So if you really got to write some fast ass Rust code.
I'm familiar with Parking Lot. I'm not familiar with the Tokyo one, but I have used Tokyo for async stuff.
Yeah. And we can decal and all that crap later. All right, so now we're going to talk about how all of this stuff is plumbed under the hood, and this is dragons again. So this, you could have put this chapter with the borrow collector, and we could have talked about all the stuff at the same time, because it's essentially a recreation of a lot of the same ideas. With the borrow collector, right, we have this concept of copy and clone, right? And if we copy it, we just simply say, I need to take all of this data, and I need to duplicate it, byte by byte. If we clone it, we can implement any series of complexities on cloning, because cloning tends to be something you implement yourself. So These two traits convey similar kinds of information as copy and clone, right? Copy and clone is about, is this thing with a single process application safe for me to make a byte-by-byte copy, or do I have to do more work? When would you have to do more work is a logical question. So you may have to do more work in, let's say that you have a database handle and you want to make a copy of that. It doesn't make much sense to take a byte-by-byte copy of a database handle. You're going to want to do something else, like establish another connection to a database. That's how you copy a handle, right? That is going to require a whole ton of work. So a database handle won't be copied, it will just be cloned. Well, now we have these different traits, send and sync, and what do? Well, send is about whether or not you can move that data type to a different thread, right? You can't always do that. Why? Because some types are not capable of having both the thread read and write to them and something previous or in the future read and write to them. Those types are not safe for that operation. One example of a complex type that you can't send, and the biggest example would just be RC, which we just covered. Right? RC cannot be moved from one thread to another. That's why we got the error. Well, internally, what actually happened is Russ said this RC thing, this reference counted thing, doesn't have send on it. So I can't give it to another thread. If you could give a reference counted variable to another thread, what would happen? We just saw that, the problems with that, right? When that thread exits, would it clean it up? What if it exits before? What if it exits after? And all these types of questions come into play. So the type is not sendable. Sync is also another complexity here, and sync is going to be related to whether or not you can share a reference between multiple threads, right? So let's say that you have a vector of bytes, and that represents your picture. Are you going to be able to give a reference to those bytes to different threads? Maybe, maybe not, right? It depends on how that vector is implemented under the hood. So what you can say is there's a relationship between the two, and if something can be sent, then a reference of it is always sync. So that's how that works. And again, this is, this may not make sense right away. It's just to introduce these ideas, right? If you want to know more about send and sync, and you really want to know, like that's something you want to learn thoroughly, the book I suggested to Josh is where you want to go, probably even more so than me, because I struggle with this a lot, and if you look at my Stack Overflow, you'll find multiple different questions I asked on this. In fact, the book I suggested to Josh made a typo, and I found that. So even the guy that wrote the book made a mistake on this. And that is easily the best book on this topic. So what I'm trying to say here is there are really good resources for this stuff outside of me, because this is very much Dragons. The first one I would suggest is the Necronomicon, because that's like the free book. I mean, the Rustonomicon. Play on words, the Necronomicon. The Rustonomicon covers sync and send very well. Nope. I think that's what they call it. Isn't it called Rustonomicon? Rustonomicon. There it is, the Rustonomicon. There we go, concurrency, send and sync. So they cover this in their book, which is, I would say, a better description of them. And then Josh has got the canonical text on that in the Programming Rust 2nd edition book. And then you're still going to have to ask questions because, well, I mean, this is complex. Talking about, generally speaking, the most complex topic in the most complex language is going to be multi-threading and Rust. And then here's the kicker: implementing send and sync manually is unsafe. So and they also went to the Rustonomicon, so I'm not doing any of this shit. Here's another catch here, why I probably don't know this stuff as well as I need to know it or should know it, especially when I'm teaching it. It's because you never do it, right? I already told you, I don't ever do any of the things I taught you today. Generally speaking, professional Rust users and novices alike will just go to Tokyo. You'll never use any of these things because they're usually slower, they tend to be a lot more complex, and the ecosystem isn't built on top of them. We have an ecosystem, simplicity, and speed in the userland library Tokyo. Right, and the non-core, I should say, non-core library Tokyo. But this idea of send and sync, what can I send to multiple threads, and can I send a reference of it to multiple threads, that is never something you're gonna work with. I've never once implemented these traits. I just know what these traits do, so when something complains, I know how to fix it, right? So all of these types of things are mostly about fixing problems with building concurrent code, not actually making your structs send in sync. Just like you, generally speaking, won't ever implement your own copy. You just do derived copy, and it works. If it doesn't work, and you want it to work, I don't even know how you do it, right? If derived copy doesn't work for you, I don't know how to make a copy work. And then that's it. We're into the fearless concurrency. Hopefully, we're all still fearless.
Why is it called fearless concurrency?
Because Rust avoids a lot of like headaches that come with other languages like data races and things like that, like C.
Headache-free concurrency?
Yeah, pretty much.
I got you.
I will say this, that this is the most complex topic in the most complex language. There's no doubt about that. However, in any other language, which is going to be simpler than Rust, this is harder. What do I mean by that? I mean that you will find many orders of magnitude more C programmers than Rust programmers, because C is a very easy language. You can learn C very easily. If you look at the amount of C programmers that have ever written multi-threaded code, it is a fraction of them. I would probably take a guess on the order of maybe 5% tops of C programmers have ever written multi-threaded code. Now, if you look at like Rust programmers, right, there's very few of us, and learning this shit is terrible, right? This is very difficult. This language I can't even stress to you how not user-friendly the learning process of this language is. That's why everyone fails at it. My first question on Stack Overflow was in like 2015 on Rust, and then I failed, and then I failed in 2017, and then you fail on this one a couple of times. Haskell's probably also like this. This is intimidating. However, if you understand Rust, my guess is upwards of maybe 30 or 50% of Rust users have written multi-threaded code. So the learning curve on Rust is really weird compared to other languages, because it's very difficult for beginners and it's very easy for experts. When you can cross the Rubicon and you say, I've learned Rust, it is easier to write multi-threaded code in this language than in any other language. And I mean that, even if this is the most complex part of Rust, which is, in my opinion, the most complex language to teach.
I would be a little inclined to disagree with like part of that statement being that like Rust is a really difficult language to learn, like learning curve wise. Coming from having learned JavaScript and Java, the user tools that come with Rust, like this is my first ever job was in Rust. It's the only programming job I ever had. Up to that point, I only had 9 months or so learning Java and JavaScript. And coming into Rust and getting all of this, like, oh, we get inlay types, we get inlay errors, we get a really friendly compiler that tells me exactly what went wrong and how to fix it and where. I felt like really comfortable with it really, really quickly. Maybe I'm just the oddball here, but I just found it to be like this godsend of a language. I was just like, oh, thank God, somebody out there is doing something to help programmers who are just getting into the space. At least that was my thought process learning Rust. I didn't feel like it was a high barrier to entry or that it was intimidating or difficult necessarily. I felt like that with Java and JavaScript because the error messages weren't helpful. It could be a slew of things going wrong through code. Yeah, just in general, those are my feelings about it. But I do know that a lot of people agree with you that it is difficult. But I don't know. That's just how I felt about it.
I mean, there's always a first time you hear that testimonial. I will honestly say that is the first time I've ever heard that. This is the second class that we've done, and I will say that the vast majority of people's experiences are not going to be like that. And while all of the errors and this kind of stuff are really great for Rust, there are some real shit stains in Rust errors too. I mean, for even the most basic things, right? Like, for instance, Axum's error messages are so convoluted, they wrote their own macro to reprocess them. And the macro is horrible. Like, I mean, I've got bug reports on the macro where I'm like, what does this even mean?
I found a way around macro, like, in order to get macros to like print the error messages a little more cleanly, there's a way that there's like a cargo tool that you can use to expand the macro so you can see what it turns into. And then from there, if you say you use Rust Analyzer, like most people do, or a cargo watch, then you could copy that from a text file that you sent it to, paste it in, and then that is a way of debugging it and getting a more clear error message. Maybe a clunky way of doing it, but macros are really hard, so.
I mean, I also think there's just some, there's just gonna be some words that I don't wanna like shit all over the language. There are definitely some examples I can give you where there's no way around it. You're just gonna have bad error messages. And even if we make the assumption that the error message is the only thing we're gonna judge the language by, I would say that for advanced projects, you can still find hit or miss things. The advantage to Rust, in my opinion, is that you get these compile time errors, but at the same time, like, Rust is so complex that, remember, there's a lot of people that have this argument. Remember when we talked about garbage collection, what did I tell you? I fall very hard on one side of it. Ignore this problem entirely, right? That's what my advice was. Clone everything, copy everything, get your programs up and working so you don't get frustrated in the language. When you do that, it becomes very difficult to move to something that is running through the garbage collector. That process is remarkably difficult. There's just a lot of stuff with Rust that you're gonna butt your head up against, that there's nothing like that complexity in any other language, And that's a really good conversation to have. I don't wanna tar people's impressions of Rust by telling about all the different words that they may run into. But it's a hard language. It's the only language that's compiled that will allow you to do things like threading with ease. And the very majority of you that learn Rust and want to do it will be capable of doing it. You'll have a lot of market value because of it. It makes really small and fast code, and it is in every way, shape, and form, in my opinion, better than C, except for the learning curve. But if I was going to teach this to a university of students that I wanted to get a job afterward, I was preparing them to. If I teach them Rust or Python, I would teach them Python. Because the chances of catastrophic failure learning Python are so much less. It's a massively easier language to teach, in my opinion.
Well, Python doesn't have a compiler, right? It's a non-compiled language and it doesn't have strong types, right?
Well, you could argue that Java also doesn't have a compiler. But what I would say here to this is, when you're comparing languages for simplicity, do you want to only compare the languages with a compiler? Because then you're comparing Rust against what? C? C++?
Yeah, I mean, I think I'm meaning it more in sure, it's user friendly out of the gate necessarily, but it doesn't help you catch problems as effectively, right? So
you have to ask for the task at hand.
Yeah.
Most jobs are just passing JSON data between some UI to the database. You don't need a serious programming language for that.
Right.
What you're doing is message passing strings between UIs and databases.
Yeah, I guess I'm thinking outside of the scope of what you were saying, which was, job market availability and
most job
learning
markets
curve.
are
Definitely Python would be a much easier language to learn than Rust.
Python, Carroll, Ruby, PHP, any popular language. And if you look at the TOB and you look at the top 20 languages, in my opinion, the only one that you could even make the argument for that is more complex than Rust is C++. And I'd probably buy it there. C++ is, because that's just so old, it's got so much different shit going on.
I had to read some C++ to help a friend who was taking a CS 101 course at a local college, and they were teaching C++, and I was like, wow, that's really weird that they're teaching you C++. She was like, yeah, it doesn't make any sense to me, so I helped her, but yeah, I can agree that it was a little bit strange to read it. The syntax was weird.
It's also it's totally different too with the onboard complexity of Rust, who you get that wants to learn it, and how many people will not make it through, even this book. I would not say that the one that Josh has got, this Programming Rust book, 1,000 times better and more comprehensive, much more scary than this book. This is the easy book for
Yeah, I
Rust.
would feel very intimidated if I hadn't gone through most of this book before starting that one.
Yep, and if you were to say what is the best method of teaching Rust, while I probably wouldn't say this book, I would say that if it wasn't for rustlings, I feel like the language would be having even more difficulties getting adopted.
I enjoyed rustlings, but I did it after I already knew most of the language. How I really learned Rust was I got hired as an intern to document the compiler of another language written in Rust. And so I had to learn about compilers and parsers and all that stuff that I had no knowledge of. And, you know, read through, I went through all their lints. I was their linter. They had like almost 1,000 lints. So I went through all their linting. So I think maybe because I was exposed to all of their error handling and like how the language was used up front and having to read a lot of documentation for several months, I think maybe that's why it was easier from the get-go for me. And I used the book more as a reference instead of just reading it straightforward and trying to build something new with it. So maybe that could be a reason.
You said you were trying to learn Rust, right? And you said you had some difficulties with how to rewrite the string.
Yeah, so like most of it makes sense to me. A lot of things translate fairly easily from other languages, but strings in particular have been like a real pain because, and I know it's just the difference between pointer and not pointer, but there's like 4 different kinds. There's like str ampersand, string ampersand, whatever,
Sure.
and none of them are compatible with each other, and it's such a pain every time I have to touch strings.
I mean, even that, like, let's take that, right? I've heard that multiple, that's probably maybe the 10th time I've heard string complexity. And I've asked questions on strings myself in Stack Overflow. So, I mean, I've had all these problems too. But, like, let's take strings and you take some, like, how I have to teach that, right? If I want people to understand strings, I would say something like, a string slice is the ampersand string thing, which is fundamentally different from a capital string, which is stored on the heap, different part of memory, right? And the capital string, right, can be provided to anything that takes a string slice. I mean, you just get through all that, and then they're like, what in the fuck is that guy talking about? And I have just covered, like, what, 4 different string types that Rust has got. I'm trying to think, there's nothing else that I can get that kind of, like, face of, what are you talking about, than Rust. And then you go into, like, details of Rust, like, you Rust for 2 years or something like that. You say, I want to communicate with the C language library. Okay, well now you have FFI strings, now you got another one, and then there's even more, you know, like there's more native, there's a lot of complexity here, you know, no doubt. And then there's other types of string types for Rust you can find on trace.io, you know, yarn, and things like that.
I might be another one of your anomalies where I actually like how they differentiate between strings, and I found it helpful, but that's really just maybe the way I'm using them, and it's the case that I have with them. Maybe later down the road I'll think differently, having bumped into something else, but like OS string for whenever you're doing something with like communicating with an application from your terminal or something, or like I feel like the differentiation helped me understand similarly to how, like, instead of seeing like a say like a variable that's named S or something like that, where it's a single character variable, that's not very helpful, but having like a specific name for it kind of helped me like identify what it was for. I feel like the same when I see those kind of things where they're like, they have a very specific name and like there's a reason for it. But again, like I can understand, like coming from a simplicity standpoint, that doesn't help a lot of people, so.
Yeah, and then if you put something in quotes, you get an error message telling you that you need a string there. So you have to call .toString on the string you provided. And then the error message is like, this isn't a string. And then what they mean to say is this is a string slice. It's not a string. You have to call .toString on a string. Like, why doesn't that implicitly coerce? I don't actually know the answer to that myself. It's a user interface decision. They could have made it work that way, but they didn't. Probably because it requires moving to the heap. They don't want anything to implicitly move to the heap.
Yeah, they want to give you the option to decide how you use that data. Yeah.
But there's only one option. If you provide something in the string slice, right, to like, let's say like here, let me give you an example, right? Let's let the code talk, it's easier. Okay, we're gonna go cargo new HLUG. We're gonna create a new thing called HLUG, and I'm gonna go down here into HLUG, and then we're gonna go source main. Okay. Let's say that I create a struct and we call it foo, and then foo's got one thing in here called bar, and it's a string, and it owns it. Here's an example of where Rust would be weird, and I can say here, there we go. Okay. So why doesn't that quote foo implicitly convert it to a string stored on the heap? It knows at compile time that this doesn't make any sense. It knows what the user wants. But the error message is try using a conversion method. The error message is actually a little bit more even obtuse there. Cargo build, right? Try using a conversion method to string, expected struct string, found string pointer. Why isn't Rust smart enough to know that the only thing you can do there is to put it on the heap to make the struct own it?
Well, I mean, so the Rust-like answer would be that it doesn't know the lifetime of foo, right? You're giving it information. It may be able to infer that you meant to put a string there, and you gave it a string slice. But you know, I think that that's what it is. It's two different types, and you gave it the wrong type. It's trying to help you by giving you like the method to change it to the type that belongs there. I know what you're trying to say, but that's the only Rust-like answer I can give you.
What I'm saying is what I want here is not this, because this thing is really stupid. Here's how I would tell you what I want. What I want is the quotes here, right? Anyone want to try to describe what quotes you're doing here? What are the quotes doing in this example? People don't actually think about quotes doing something, right? Because we're used to looking at it as a syntax. But what do the quotes do?
So it's an opening and closing delimiter, sort of, right? So it's opening.
And that's if you're writing a parser, it's that. Well, here, right, what I'm looking for is the opening and closing quotes are a capital string constructor, right? It's like providing a piece of data to capital string.new, right? That's what the quotes are actually doing with Rust. That's syntactic sugar to construct a string. You can also construct a string using, I think, str exclamation points and macro, right?
Does that macro exist? I didn't know that macro existed.
I think it does. But the point here is that this is essentially, it's kind of like a syntactic sugar or a macro that is actually part of the parsing structure, right? So they've actually said this is what, and by the way, the opening and closing brackets are also syntactic sugar. What are they doing? Think about it. Constructing a
Closure?
array. Curly brackets closure. Brackets array, right?
Oh.
So you can.
The str macro is for owned strings. So it would actually be a method to solving this issue. Like if you wanted it to have like a string with capital S, string, so the str exclamation point, at least looking it up on.
We'll take a look at it. We'll take a look at it, right? But what I wanted to say here is that the opening and closing double quotes are a string constructor, right? But they're not a string constructor. I'm sorry, let me change it. They're not a string constructor for a capital string. They're a string constructor for the lowercase string, right? So they're actually taking that thing and they're storing it in a piece of memory, those bytes, and they're storing them in a piece of memory as easy as the problem here is that what you want is something like a double quote that makes one of these instead. That's what everyone wants. If I provided that to you, it would make sense. Because then I would have an actual method to create a literal string on the heap. Like that's a language feature, right? Now what you would ideally have is something that does that, creates a literal string on the heap, and then you would be able to say, given the context, does this need to be created on the heap? If not, create it on the stack, right? And it could fall in between those two. And that's how, there's other languages that do that, but that's what people actually want. And Rust is telling you, when you use a double quote, I can't build a capital string from that, because that requires copying bytes to the heap. I don't have the language facilities to do that. That's like a philosophy of Rust, that that doesn't happen. Copying is never an implicit operation in Rust, right? Copying those types of data. So Rust tries to make it explicit everywhere. Now in a language like C++, that is everywhere, right? Copying is how that language works. So, and that's why, by the way, in C++ you can make a small mistake and you copy, your whole megabytes of data from the heap. But Rust says it's always got to be explicit. But what ideally you'd have is you'd have like its own string constructor that would have like something like double quotes, and then it would just know that for you. And then you'd have something that could pick between the two of them, given the context. Let's try the capital strn thing. So you're saying here, you're saying that'll work?
So let me check the syntax really quick again. Yeah, that will work, but it'll give you struct string. I think that's maybe one thing that maybe people don't think that like the difference of them, right? Like capital S string is a struct.
Where are you finding this macro? Where was this macro defined again? I forget.
And I just looked up str macro rust, and it came up docs.rs. Allows you to conveniently create own strings similar to that.
Yeah, but this is not actually part of the standard library. This is a crate.
Oh yeah, it's a crate.
But I think there's actually a string macro in the standard library. It's very simple.
Let me just look up the standard.
Anyway,
Are you talking about stringify?
no, I thought there were this. I thought that this functionality was in the standard. Maybe I'm wrong. Maybe this is the only place it exists. But this is also an area where there's no congruency here. We have this let b equals bec, which we use all the time, but there is nothing like let s equals string, right? So here, they're creating a macro that does this. And then it does, yeah, this is the one I'm telling you. Anyway, this kind of stuff bothers a lot of new people, and it's complex, and you don't have this complexity in the writing plan. So, anyone have any questions on any of this? You want to see anything with string? You have any specific questions you want to go over?
I can't think of anything off the top of my head.
The only thing I would say to it is, when you're creating functions, always use the string slice, ampersand str. Cool. All right, awesome. That's all I got for you. So we'll come back next week. I think we got, let's look at the chapters and tell me if we're interested in doing them. Because I think as we go through this, we're getting more and more into the weeds. Object-oriented programming features of Rust. Are you interested in this, Josh?
Can we look at the individual little
Characteristics of an object-oriented language. So this is going to compare objects, which store state in object-oriented languages, to structs, and it's going to talk about why structs are different, right? So we make arguments in Rust like objects are stupid, you shouldn't do that. We make these arguments because object orientation includes different things that Rust does better, right? Like, there's been a migration to get rid of inheritance. If you don't know what inheritance is, this will introduce that concept and show you that Rust doesn't have it, so you know why it's different.
I understand what inheritance is.
Using trait objects that allow for values of different types. This is going to cover how we use, in a lot of languages, we use objects as the type. This is going to talk about how you can specify one type to accept multiple different structs, when that type is a trait object, right? So here they're saying this components here is a vector of things that implement the draw trait.
Gotcha. I think we went over that a little bit.
That's very cool. I've seen stuff like that a handful of times, but I've never actually gotten to use it that way.
The most popular place you'll see this is in functions that either accept or return an error object, because the error object can implement std error, which is a trait, right? And then your function, you'd only know that whatever I'm receiving needs to implement error. Then I can say, if you die, throw the error up.
Gotcha.
So you'll see that very frequently. This function returns something that implements this. Let me see what something has to do. I'm pretty sure we've already implemented traits before.
Do we have?
The most prominent trait you'll probably be implementing is going to be things like display. defining post and creating new instance. So here we're implementing, they're showing you how to structure a program. That's what this is.
Okay, so basically just
This looks
going
like
through input blocks and just adding your own methods to
Yeah.
things.
Yeah. Which again is how the whole entire language is working, right? You take your data and you say what you need, and then you just keep creating implementations out of it, going through the behaviors you want.
Gotcha.
And then, so I don't know what you think about that chapter, we can cover it or skip it. Pattern matching, literals, okay, so this is gonna be on, when we have this match block, this is used everywhere in Rust, and we've only really touched the surface of that functionality.
Okay.
There's a lot. So patterns in Rust can be what they call irrefutable and then used in other areas, or they can be refutable, which are like these patterns that may or may not match or apply. And I think we covered both of those. And then advanced features, I can probably tell you this would be a total waste of time.
Gotcha.
Well, no, the iterator, I take that back entirely. The iterator is extremely useful. I think we've covered that. The iterator for counter, this is all good. The add for point, that makes sense. So unsafe Rust is stupid. We should, there's a whole book on that called the Unsafe Rust book. Advanced types, the new type pattern. This is actually pretty useful there too. Advanced functions and closures.
Macros.
Yeah, okay, this is talking about how we can return things. We can't return dins because they don't know the size, so you box it when you know the size. So that's what you always see, box with dim. You can't have dim by itself.
And you know the size because the box is just a pointer to the heap, right?
That's exactly right. Yeah, 100%. And then macros. And this is like literally the worst. I mean, it's not bad. It's just that's the shortest explanation of what macros do in Rust. What they actually do is far more complex. If there's, I mean, you'll see them everywhere, and writing and using them is a lot more exhaustive than this one thing we're looking at.
I don't mind just like next class or something if we kind of just want to pick the funnest things and just go through them and.
Finish off in the next class.
If you want to, I'm down for that.
I think so, because I think a lot of that I can skip, so we can just see how far we can get the next class, and then
Yeah.
we'll end it. And then I think the next class that we're gonna do is the one for Captain Dad.
Yeah.
Yeah, he wants to do PostgreSQL. Do we have any other interest in PostgreSQL? Does anyone use Postgres? Are you interested in the class on Postgres, or are you interested in the database?
Sure.
Cool. Anyone else interested in PostgreSQL?
I have a school class over Postgres actually.
Very
So,
cool.
I haven't done it yet, but.
You can go deep into Postgres. I mean, I use that all the time. I'm a developer on that project. Cool. Well, if anyone wants to cover that, definitely give us a shout, because that'll be the probably next one we hit. I think we'll probably be like a month away. And we're gonna get our hands dirty with it.
I actually just remembered about, we were talking about atomics and locks.
Yeah.
Mara Vos, she's one of the developers for the Rust language. She just released a book
Yeah.
on atomics and locks. So if anybody didn't understand or wants more information, there's a whole book on it now.
Not yet.
It's available now. She released it just a couple weeks ago.
No. I don't think so.
Atomics and locks, it's on O'Reilly.
I mean, I pre-ordered the book a year ago. I don't have it. So I don't know when they're shipping it out.
I don't know if she's shipping it out, but she said it was available for purchase.
Interesting. Can anyone confirm that? Is that available?
I saw it on Twitter and then I followed up on finding where I could buy it from. And it was on
Are you sure you're not talking about the web book by Leap? Because there's there's a web book with Rust that I just got. It did just come out.
I'm fairly certain. Atomics, Analog.
Let's take a look
Yeah,
at
it
it.
says it's, I could buy it for $45 on Amazon. Oh, it says, but the title has not yet been released.
Yeah, I don't think it's out. I'd be curious to know where that information is, because.
Oh, it says pre-order.
Right.
I guess I misread her tweet. I thought maybe she said it was available for pre-order. Maybe that's what it was.
I think it's available in like 2 weeks though.
Yeah, see, I bought it in
Arriving January 26th.
yeah, so.
Oh, there you go. You want to wait 2 weeks?
Another couple of weeks. Wow. Rust.
complex it was.
I'm sure that book will be very advanced. But yeah.
Yeah.
Cool.
Why is there a bear?
O'Reilly assigns a random book. I think they give their illustrator discretion on it. A random animal to every book. It's like a long thing they've done. And it's actually become like almost somewhat famous in branding topics. So in the Perl community, the Perl animal is the camel. You know, and that camel book is like programming Perl. And then the llama book is learning Perl. And you know, that's how they do it. And then the books get named by that. It used to be all tech books had a theme like this. Like the compiler book was called the dinosaur book, or the operating system book. The compiler book is the dragon book, the operating system book is the dinosaur
Is
book.
that why you kept saying dragons?
Must be.
I have the dragon
The
book.
Linux handbook is a cowboy.
I couldn't figure out why you kept saying dragons during the lecture. What did I say dragons? You said dragons.
He's talking about dragons by dealing with like.
Oh, there's oh no. I mean like that, when I say
It's
like there's
a
dragons in
dragon,
there,
like you have to fight
that's a traditional thing. This area is a lot more scary than the other areas, you know?
Okay.
Like you don't wanna go poking around in this shit.
High level enemies. Gotcha.
Yeah, high level enemies, exactly. Because like, there's a lot of this book that touches on topics that I know of, but I myself don't mess with, like the send and the sink tree.
It's like shark infested waters, like it's scary to go and read.
And if you read source code too, you'll typically find developers write there be dragons here, and then that's
Okay.
like your way of warding off other developers who think they can mess with that code. So I mean, if you're writing code,
Mind game.
or you find code that is brittle and breaking it will cost a lot of money, then you would typically say there be dragons here, and then no one's gonna try to refactor that code, it will just sit there,
Okay,
you know?
understood. Didn't know that.
Yeah,
With the hours wasted counter at the top.
exactly, hours wasted. Yeah, very good. Best way to quantify code debt. Anyway, cool. Well, we can go on back in the other room and you know, appreciate that. Awesome. Thank you.
Good class.